for today's video, we're going to talk a little bit about linear transformations and what exactly is a linear transformation and how do we go about using them in proofs. And to do that, we're going to use a problem from our textbook in section 2.7, number 84. And this problem says that if we have the linear transformations t and u that are from Rn to Rm, they are functions and c is a scalar, then we're going to define t plus u from Rn to Rm by the equation t plus u of x, a vector x, equals t of a vector x plus u of a vector x. And this is going to be true for all vectors x in Rn. And they want us to prove that if we know t and u are linear, then the transformation t plus u is also linear. And before we get into the proof, obviously, we need to talk about what is a linear transformation. And a linear transformation is simply a function that relates something in one set to something in another set. Okay, so if you think way back in your other math classes, you've probably talked about the domain and the codomain. And what we're going to be doing in this example is taking a vector that exists in our domain, R of n, and we're going to be relating it somehow. That's what our function is going to do. We're going to make an association between this vector in Rn and a resulting vector in Rm after we do the transformation. So the definitions that we'll be using in order to do that today. So in order to define a linear transformation, we need to have S1 and S2 be subsets of a vector space. So we're going to be using Rn and Rm. Then we have a function f of x here in the definition, and that will be represented with a t. Don't get confused, these are the same thing. T, u, these are just variables representing a transformation, which is another word for a function. And so for any vectors v and u in our domain of Rn, and any scalars c that are in the real numbers, then we know that both of the following are true. So if this is linear, then both of the following are true. Okay, so f of the vectors u plus v is going to equal f of the vector u plus f of the vector v. And this is called preserving vector addition. That's how we're going to describe it when we do our proofs. We're going to say that if this is linear, it preserves vector addition. In addition to that, we have to preserve scalar multiplication, which means that our function with any constant times the vector u is going to equal, if we pull that constant out, it's going to be equal. So we'll have c times f of u is going to be equal in order to preserve scalar multiplication. Now, you can also combine these two, as I've shown at the bottom here. You can also combine these two into one step and use two scalars. But for today's video, since we want to kind of see the whole process here, we're going to do them individually. So as usual, before we get started, we're going to want to figure out what it is we already know, right? So we're going to start with what they've given us in this problem in order to start our proof. So we'll start by letting the transformations t and u be from Rn to Rm, be functions, and let c be a scalar, such that the transformation t plus u is defined as t plus u of vector x equals t of the vector x plus u of the vector x for all x in our domain of Rn and for all the scalars in the real numbers. Just before we go any further, just keep in mind here that when we're talking about t plus u, at this point it's no longer two transformations. After we do this sum, you can consider this one linear transformation, one transformation, right? So we could just as easily call this S instead of t plus u. We could call it Q. We could call it smiley face. It doesn't matter. It's just important conceptually that you think of this not as two separate transformations, but as one transformation, okay? So now that we've established what we've been given, what we need to do is remember this is an if-then proof. So we're going to assume our if is true. So if t and u, our transformations, are both linear, then we know that vector addition must be preserved. So we're going to use our formulas to show that here. We're going to show that if we know t is linear, then t of u plus v must equal t of the vector u plus t of the vector v, and the same for the transformation u. So using the definition that we were given, we can now put this together and see that the transformation t plus u of the vector u plus v equals the transformation of the vector u plus the transformation of the vector v plus the u transformation of the vector u plus the u transformation of the vector v. And all we're doing in these next two steps is using our associative distributive properties here, or our associative and commutative properties, to rearrange this, because we're looking for this to be in a specific form to fit our definition. So even though this might look a little bit complicated, all we're doing here is rearranging the order and rearranging our parentheses to get it to the form of the vector for the transformation t plus u of the vector u plus the transformation t plus u of the vector v. And of course, that's what we're looking for our definition of preserving the vector addition. So we know that this half of proving it's linear is true. So now we can go on to the next half, which was, remember, we're going to show that it preserves scalar multiplication. So since our transformations t and u are linear, they also have to preserve scalar multiplication. So we're going to list our formulas for that. So t of a constant times the vector u must equal that constant times t of the vector u, and the same for the transformation u. So that tells us that if we have t plus u, the transformation, the single transformation, t plus u of the constant times the vector u, then we're going to plug these into this now. And we're going to have the transformation t times c times the vector u plus the transformation u times c times vector u. And what we're going to do now, we can pull that c out. Remember, we can pull that c out. So we're rewriting it with the c pulled out the front. And in our next step here, what we're doing is just combining these, and we're going to pull the c out from both of them totally and have it on the outside. And since that we know that our definition of t plus u was given to us as t of the vector u plus u of the vector u, we can substitute that back in. And now what we have what we're looking for to prove that the scalar multiplication is upheld, is preserved. So we're left with a constant times our transformation t plus u of u is equal to the t plus u transformation of the constant times the vector u. At this point, we've actually proven that it preserves vector addition, and we've proven that it preserves scalar multiplication. And remember, those were our two criteria for proving that this new transformation is linear. So at this point, we'll wrap it up, and we'll just say that thus t plus u is linear, and we've done it.